What if I told you that the device you're watching this on right now, your smartphone, your computer screen, is doing something that breaks the fundamental laws of physics as we understand them? And not just bends them, actually shatters them into pieces that scientists a century trying to glue back together? Right now, photons, particles of light, are hitting your retina. But here's the thing that will keep physicists awake at night. Those photons don't exist in time the way you and I do. From a photon's perspective, if it even has one, it is created and destroyed in the same instant, even if it travels for billions of years across the universe from our perspective. And that's just the beginning of the nightmare. Light is simultaneously the most studied phenomenon in all of science and the least understood. We've built entire civilizations on technologies that harness light, from fire to fiber optics. Yet when you ask a physicist, "What is light, really?" watch their face carefully. You'll see a moment of existential dread flicker across it before they start talking about wave-particle duality or electromagnetic radiation. But those aren't answers. They're linguistic shields protecting us from a terrifying truth. We don't actually know what light is. We know what it does. We can predict its behavior with stunning accuracy. But what it fundamentally is? That question has broken some of the brightest minds in human history. Here's something that will blow your mind right now. Light doesn't experience distance. A photon that travels from a star 13 billion light years away doesn't experience that journey. From its reference frame, if we can even use that term, it is emitted and absorbed instantaneously. Space and time literally collapse to zero for light. So what does that mean? Is light not really traveling at all? Are we the ones moving? Is the universe itself an illusion created by the fact that we're not light? Before we go further into this rabbit hole, and trust me, it goes deep, do me a favor. Hit that like button right now. Not later, right now. Because what I'm about to share with you will fundamentally change how you see reality, and YouTube's algorithm needs to know this matters. Subscribe if you haven't already, because we're going on a journey that will take 3.5 hours, and by the end, you will never look at a beam of sunlight the same way again. Also, drop a comment telling me, what country are you watching from, and what time is it there right now? I want to know where in the world people are ready to have their minds bent into pretzel shapes by the mystery of light. Are you in New York at midnight, Tokyo at noon, Mumbai in the evening? Let me know. Let's start with what seems like a simple question. How fast is light? You probably know the answer. 299,792,458 meters per second, or about 186,000 miles per second. We usually round it to 300,000 kilometers per second for convenience. In 1 second, light travels far enough to circle the Earth 7.5 times. But here's the twist that nobody tells you in school. That's not just how fast light moves. That number, the speed of light, which physicists call c, isn't really about light at all. It's the speed of causality itself. It's the speed limit of the universe, a maximum rate at which cause and effect can propagate through space. Light just happens to travel at this speed because photons have no mass. Think of it like this. Imagine the universe as a computer simulation running on some cosmic hardware. The speed of light is the processor speed, the refresh rate of reality itself. Nothing can happen faster than this, because nothing can update faster than the universe's frame rate. Now you might be thinking, okay, but why exactly that number? Why not faster or slower? And here's where things get weird. That question might not even make sense. The speed of light isn't fast or slow. It just is. It's the fundamental exchange rate between space and time. When we measure it at 300,000 kilometers per second, we're really saying, this is how much space equals that much time in the universe's conversion chart. You can't ask why without stepping outside the universe itself. But let's back up even further. What was the first time a human being actually wondered about light? We don't know for certain, but we have records. Ancient Greek philosophers were obsessed with vision and light. Empedocles, around 450 BCE, proposed that vision worked because fire particles emanated from the eye and mixed with light from external sources. Insane, right? Except he was half right about something important. He understood that light and vision were two separate phenomena that had to interact. That insight was actually profound. Plato thought the eye emitted its own light that mixed with daylight. Aristotle disagreed. He believed light was the actuality of the transparent, whatever that means. The ancient Greeks were fumbling in the dark, quite literally, trying to understand light by thinking about it philosophically. Then came Hero of Alexandria, around 60 CE. He asked a practical question. Why does light reflect off mirrors at equal angles? His answer reveals something fascinating about how the ancient mind worked. He said light takes the shortest path because light doesn't want to waste time. He attributed intentionality to light as if photons were making decisions. And you know what? Modern physics has a formulation that's eerily similar. It's called Fermat's principle of least time, developed by Pierre de Fermat in 1662, and it says that light takes the path that requires the least time. Not the shortest distance, the least time. And when you calculate which path takes the least time, you get the correct path light actually takes, including how it bends when entering water or reflects off surfaces. But why? Why would light choose the fastest path? It doesn't have a brain. It can't evaluate alternatives. Yet it behaves as if it somehow knows all possible paths and picks the optimal one. This is the first hint that light is doing something much stranger than just moving through space. Let's talk about Isaac Newton for a moment, because his ghost still haunts this conversation. In 1704, Newton published Optics, where he argued that light was made of particles, little bullets of light he called corpuscles. Newton wasn't dumb. He knew about diffraction and refraction. He knew light bent around corners and changed speed in different materials. But he thought particles could explain all of this through mechanical forces. Why did Newton think light was particles? Because particles made sense to him. You could calculate their trajectories. They obeyed nice, clean mathematical laws. Newton was the guy who just explained planetary motion and falling apples with the same set of equations. He wanted light to fit into his mechanical universe, but there was a problem. A Dutch physicist named Christian Huygens had a different idea. In 1678, he proposed that light was a wave ripples propagating through some invisible medium that filled all of space, which they called the luminiferous ether. Now, here's what's important to understand. Both Newton and Huygens were right, and both were catastrophically wrong. But nobody would figure that out for another 200 years. The 19th century was when things got really interesting. In 1801, an English polymath named Thomas Young performed an experiment that should have settled the debate forever. Young's double-slit experiment was beautifully simple. He shone light through two narrow slits, cut close together in a barrier, then observed the pattern on a screen behind it. If light was particles, like Newton claimed, you'd expect to see two bright bands on the screen, just light bullets piling up after passing through each slit. That's not what happened. Instead, Young saw multiple bands of light and dark in interference pattern. The light was acting like waves in water. When two wave crests met, they amplified each other, bright bands. When a crest met a trough, they canceled out dark bands. Light was interfering with itself. This should have been the end of the story. Light is a wave. Case closed. But keep watching, because this is where the nightmare truly begins. Before we continue, I need you to understand something. Everything I've told you so far is the comfortable story, the version they teach in high school, the sanitized narrative that makes sense. But what I'm about to reveal to you next is where the comfort ends. We're about to enter territory where even professional physicists start using phrases like shut up and calculate, because the implications are too disturbing to think about for too long. What happens when you send light through Young's double-slit experiment one photon at a time, so only a single particle of light exists in the experiment at any moment? Logic says you should get two bands, right? One particle can only go through one slit, but you don't. You still get the interference pattern. Somehow, a single photon is interfering with itself. It's acting like it goes through both slits simultaneously. And if you try to detect which slit it goes through by placing a detector, if you simply try to observe which path the photon takes, the interference pattern disappears, and you get two bands like you'd expect from particles. The act of observation changes what light is. This isn't philosophy. This is experimental fact, repeated millions of times in laboratories around the world. The universe literally behaves differently when we're watching. Stay with me? This gets so much stranger. Let me introduce you to the man who broke physics, Albert Einstein. Most people know Einstein for relativity, but in 1905, his miracle year, he published a paper that would win him the Nobel Prize and simultaneously destroy the comfortable wave theory of light that had dominated for a century. Einstein was trying to explain something called the photoelectric effect. When you shine light on certain metals, they emit electrons. Simple enough, but there were weird quirks. If you increased the brightness of the light, you got more electrons, but each electron had the same energy. If you changed the color of the light to a bluer wavelength, each electron suddenly had more energy, even if you made the light dimmer. This made no sense if light was a wave. Waves should transfer energy gradually. A brighter wave should give each electron more energy. But that's not what happened. Einstein proposed something radical. What if light came in discrete packets quanta of energy? What if Newton was right, and light was made of particles after all? These particles, later named photons, each carried a specific amount of energy determined by the light's frequency. Higher frequency, bluer light, meant more energetic photons. Brightness was just how many photons you had. The photoelectric effect suddenly made perfect sense. One photon hits one electron, transferring its energy directly. More photons, more electrons. More energetic photons, more energetic electrons. But wait, Young's double-slit experiment proved light was a wave. Now Einstein was saying it's particles. Both experiments were correct. Both couldn't be true simultaneously. Or could they? What if I told you that the entire concept of wave versus particle is a human-made distinction that nature doesn't actually care about? This is called wave-particle duality, and it's not a property of light. It's a property of our limited human perception trying to understand something that doesn't fit our macroscopic categories. Think of it like this. Imagine you're a two-dimensional being living on a flat surface, and someone passes a sphere through your world. First, you see a point appear, the sphere touching your plane, and a circle that grows larger, reaches a maximum size, shrinks, and disappears. You'd argue about whether the object was point-like or circle-like, never realizing it's a sphere, something your dimensional perspective can't fully grasp. We're those two-dimensional beings, and light is the sphere. The physicist Niels Bohr proposed something called complementarity. Light exhibits wave-like or particle-like properties, depending on what kind of measurement you're making. It's not that light is a wave or a particle. It's that these are two complementary ways our measuring devices can interact with whatever light actually is. But this raises a disturbing question. If light's nature depends on how we measure it, does light have an independent existence at all? Or is reality itself somehow incomplete until an observation collapses it into one form or another? Here's where I need to introduce you to quantum mechanics. And I'm going to be honest with you. Nobody, not Einstein, not Bohr, not the most brilliant physicist alive, today truly understands quantum mechanics. We have equations that work with astounding precision. We've built transistors and lasers and quantum computers based on these equations. But what they mean? That's where consensus evaporates. The quantum mechanical description of light uses something called a wave function. This is a mathematical object. It describes all possible states a photon could be in its position, momentum, energy, polarization, everything. But here's the critical part. Before you measure the photon, it doesn't have definite values for these properties. It exists in what's called a superposition, a ghostly blend of all possibilities simultaneously. Only when you make a measurement does the wave function collapse, and the photon suddenly has definite properties. But this creates an absurdity. Before you measure, where is the photon? It's not in a specific location. It's in a superposition of all locations. It doesn't have a specific momentum. It has all possible momenta at once. The math works. The predictions are accurate to 15 decimal places. But what does it mean for something to be in multiple states simultaneously? Let me give you an analogy. Think of light like a coin spinning in the air. While it's spinning, it's not heads or tails, it's both and neither. Only when it lands does it become definitively one or the other. Quantum mechanics says reality is like that coin, constantly spinning until an observation makes it land. But here's what makes this analogy break down. With a coin, we know it's always really either heads or tails. We just don't know which until we look. The coin has a definite state. We just lack information. Quantum mechanics says nitrogen monoxide. The photon genuinely doesn't have a definite state. It's not that we lack information. There is no information to lack. The photon is in a real physical superposition until measurement collapses it. This was so disturbing that Einstein spent the rest of his life trying to prove quantum mechanics was incomplete. He famously said, "God does not play dice with the universe." He believed there had to be hidden variables, deeper properties we couldn't see that determined what would happen when we measured. But experiments have proven Einstein wrong. In 1964, a physicist named John Bell developed a mathematical theorem showing that no local hidden variable theory could reproduce quantum mechanical predictions. Experiments testing Bell's inequality have been performed thousands of times with increasing sophistication. The results? Einstein was wrong. There are no hidden variables. Reality really is fundamentally uncertain until measurement. The universe does play dice, and light is rolling them every moment. Here's something that should terrify you. Every photon that has ever hit your eye, every glimmer of sunlight, every LED glow, every star you've ever seen existed in superposition, smeared across space in a probability cloud until the exact moment it interacted with the molecules in your retina. Your observation didn't just detect the light. It created the definite reality of that light in that moment. You're not just seeing the universe. You're participating in its creation, one photon at a time. Make sure you're subscribed, because we're going deeper. The next section will reveal why light doesn't experience time, and what that means for the fundamental nature of reality itself. Let's talk about time. Or rather, let's talk about why light doesn't experience it. In 1905, the same year Einstein explained the photoelectric effect, he published another paper that would overturn 3 centuries of physics: special relativity. The core insight was this: the speed of light is the same for all observers, regardless of how they're moving. This sounds innocuous until you really think about it. Imagine you're on a train moving at 100 miles per hour, and you throw a ball forward at 20 miles per hour. To someone standing on the ground, the ball is moving at 120 miles per hour, the speed's at. This is common sense. But light doesn't work this way. If you're on a spaceship moving at 90% the speed of light, and you shine a flashlight forward, the light doesn't travel at 190% light speed. To you and to a stationary observer, the light moves at exactly 100% light speed. How is this possible? Einstein's answer: space and time are not fixed. They're flexible, stretching and compressing to ensure light speed stays constant. The faster you move, the slower your clock ticks relative to someone at rest. The faster you move, the more space contracts in your direction of motion. These aren't optical illusions. Time literally slows down, and space literally shrinks. Now here's the mind-bending part. As you approach the speed of light, time slows more and more. At 90% light speed, time passes about 44% slower for you than for someone at rest. At 99% light speed, time slows to about 14% normal rate. What happens at exactly 100% light speed at the speed of light itself? Time stops completely. Space contracts to zero. From a photon's perspective, if it has one, the universe is a single point, and its entire existence from emission to absorption happens in zero time. Think about that. A photon leaving the Andromeda galaxy, 2.5 million light-years away, travels for 2.5 million years from our perspective before hitting your eye. But from the photon's perspective, its journey is instantaneous. The moment it's emitted from an atom in Andromeda and the moment it strikes your retina are the same moment. The photon doesn't travel at all from its own frame of reference. The concept of traveling implies experiencing a duration leaving point A, existing for some time, arriving at point B, but photons don't experience duration. They don't experience space. They exist in a timeless, spaceless state that our physics literally cannot describe because our equations divide by zero. This creates a profound mystery. How can something that doesn't experience space or time connect cause and effect across the universe? Here's an analogy that might help. Think of the universe as a book. You, with mass, moving slower than light, experience the book one page at a time. That's your journey through time. Light, meanwhile, experiences the entire book simultaneously. The first page and the last page are the same moment for light. Yet somehow, light connects events on different pages. A photon emitted from the sun reaches Earth 8 minutes later by our clocks. That photon carries information, energy, momentum, information about the sun's composition across 93 million miles of space and 8 minutes of time. But it experiences none of that journey. So what's really happening? Is the photon not moving at all? Are we the ones changing? Is space-time itself just a story we tell ourselves to make sense of relationships between events that are actually all happening simultaneously? The physicist Julian Barber has proposed that time doesn't exist at all, that the universe is a vast space of possible configurations, and what we call time is just a sequence of relationships between these configurations. From this perspective, photons aren't traveling through time because time is an illusion. They're just connecting configurations that we perceive as separated by time and space. But let's make this even stranger. Einstein's special relativity led to his general theory of relativity in 1915, which revealed that mass and energy curve space-time itself. Light follows these curves. When light passes near a massive object like the sun, its path bends. This isn't because gravity pulls on the massless photons. It's because the sun warps space-time, and light follows the straightest possible path through curved space-time, what mathematicians call a geodesic. In 1919, an expedition led by Arthur Eddington photographed stars near the sun during a solar eclipse. Their positions were shifted slightly because the sun's mass bent the starlight passing nearby. This observation made Einstein world famous and confirmed general relativity. But here's what nobody tells you. Light traveling in curved spacetime can create causality loops, closed time-like curves where cause and effect become circular. Near rotating black holes, the curvature becomes so extreme that theoretically, light could complete a circular path and return to its starting point. Not just in space and spacetime, the photon would arrive before it left. Does this violate causality? Can effects precede their causes? General relativity says maybe. Quantum mechanics says it depends on what you mean by cause and effect. The union of these theories, quantum. Gravity doesn't exist yet, so nobody knows. Light is breaking not just our understanding of space and time, but cause and effect itself. Take a deep breath. I know this is overwhelming, but here's why it matters. Every photon you're seeing right now on your screen traveled from the LED backlight through liquid crystals, emerged through the glass, crossed the air, entered your cornea, focused through your lens, and struck your retina all in less than a billionth of a second. From the photon's perspective, that journey didn't happen. The LED and your retina exist at the same moment in the photon's reference frame. Your vision, your entire visual experience of reality, is mediated by particles that don't experience the reality they're showing you. We're going to take a short break from the physics to ask, why has light been so hard for scientists to explain? What is it about light specifically that breaks our conceptual frameworks? The answer will surprise you. The story takes a turn in the 1860s with a Scottish physicist named James Clerk Maxwell. Maxwell was trying to unify everything known about electricity and magnetism. Scientists had discovered weird relationships. Moving a magnet near a wire created electrical current. Running electrical current through a wire created a magnetic field. Electricity and magnetism seemed to be two faces of the same phenomenon. Maxwell developed 4 elegant equations, now called Maxwell's equations, that unified electricity and magnetism into electromagnetism. These equations described how electric fields create magnetic fields, how magnetic fields create electric fields, and how they propagate through space. Then Maxwell did something that changed everything. He manipulated his equations to derive a wave equation, a mathematical description of waves propagating through space. And when he calculated the speed of these electromagnetic waves, he got a number, approximately 300,000 kilometers per second. The speed of light. Maxwell realized light is an electromagnetic wave, not something that creates electromagnetic effects, but literally an oscillating electric and magnetic field propagating through space. This was a stunning unification. Light, electricity, and magnetism were all the same phenomenon. But Maxwell's equations raised a disturbing question. Waves are disturbances in a medium. Water waves travel through water. Sound waves travel through air. What medium were electromagnetic waves traveling through? The answer, scientists believed, was the luminiferous ether, an invisible, massless substance that filled all of space, through which light propagated. This created problems. The Earth orbits the Sun at about 30 kilometers per second. If we're moving through an ether, we should detect an ether wind, a difference in light speed depending on whether we measure with or against Earth's motion. In 1887, Albert Michelson and Edward Morley designed an experiment to detect this ether wind. They used an interferometer, a device that splits a light beam, sends the beams on perpendicular paths, and recombines them to create an interference pattern. If Earth was moving through an ether, one beam should travel with the wind and one against it, creating a detectable phase shift. They found nothing. No matter which direction they measured, light traveled at exactly the same speed. The experiment was repeated with increasing precision. Same result. The ether wind didn't exist. This created a crisis. If light is a wave, it needs a medium, but the medium appears not to exist. How can waves propagate through nothing? Einstein's special relativity solved this problem by eliminating the question. There is no ether. Light doesn't need a medium. Space itself doesn't need to be filled with anything for electromagnetic waves to propagate. This is deeply strange. Every wave we're familiar with is a collective behavior of many particles. Ocean waves are coordinated motion of water molecules. Sound waves are pressure variations in air molecules. But light? Light propagates through pure vacuum through absolute nothingness. What's waving? Maxwell said electric and magnetic fields are waving. But what are fields? Think of it like this. A field is an assignment of a value to every point in space. The temperature in this room is a field. Every point has a temperature value. Electric and magnetic fields assign a vector, direction and magnitude, to every point in space, But fields aren't made of anything. They're abstract mathematical objects that describe how charged particles will respond if placed at each point. An electric field doesn't exist in the way a rock exists. It's a description of potential interactions. Yet these abstract mathematical fields can carry energy and momentum. They can push on charged particles. They have real, measurable effects. So what are they fundamentally? Nobody knows. We have equations that describe how they behave. We can predict their effects with incredible precision. But what they are, ontologically, their fundamental nature, remains mysterious. Here's something that will blow your mind. According to quantum field theory, our best description of reality, particles aren't fundamental. Fields are fundamental. The universe isn't made of particles moving through space. It's made of fields permeating all of space. Particles are localized excitations ripples or waves in these quantum fields. An electron isn't a tiny ball. It's a quantized excitation of the electron field that permeates the universe. A photon isn't a particle of light. It's a quantized excitation of the electromagnetic field. This is why light is both wave and particle. It's a wave in the electromagnetic field that comes in discrete quanta. The wave-particle duality isn't light having two natures. It's us trying to describe a quantum field excitation using our intuitive concepts of waves and particles, concepts that don't really apply at the quantum level. From this perspective, the question, what is light, becomes, what is the electromagnetic field? And that question leads us into even deeper mysteries. The electromagnetic field has a property that's utterly bizarre. Even in a perfect vacuum, with no photons present, quantum mechanics says the field doesn't have zero energy. It has what's called zero-point energy irreducible quantum fluctuations. Imagine perfectly calm water. You'd say there are no waves, but at the quantum level, calm doesn't exist. The Heisenberg uncertainty principle says you cannot have a field with exactly zero energy and exactly zero fluctuation simultaneously. So even the vacuum is seething with virtual photons particles that pop into existence for infinitesimally brief moments before vanishing. These aren't theoretical. They have measurable effects. A Casimir effect demonstrates this beautifully. Place two uncharged metal plates extremely close together in a vacuum. They'll be pushed together by a measurable force. Why? Because the quantum fluctuations of the electromagnetic field between the plates are restricted. Only certain wavelengths fit between the plates. Outside the plates, all wavelengths can fluctuate. This creates a pressure differential. Empty space isn't empty. It's full of quantum uncertainty, bubbling with potential photons that almost exist. The vacuum itself glows with invisible light. We're 1 hour into this journey, and I need to check in with you. If you're still here, you're awesome. Drop a comment and tell me, what's the most mind-blowing thing you've learned so far? Is it that light doesn't experience time? That particles aren't fundamental? That the vacuum isn't empty? And if you haven't subscribed yet, now's the time. We're about to enter the truly bizarre territory where quantum mechanics meets light, and trust me, you don't want to miss what's coming. Hit that like button to feed the algorithm and help other people find this deep dive into one of the universe's greatest mysteries. Let's return to the double-slit experiment, because we haven't fully grasped how disturbing it is. Remember, send photons one at a time through two slits, and they create an interference pattern. Each photon somehow goes through both slits and interferes with itself. But put a detector at one slit to see which path the photon takes, and the interference pattern disappears. But here's where it gets insane. You can place the detectors after the slits, but before the screen. The photon has already decided whether to go through one slit or both before your detectors are there. Yet adding the detectors retroactively changes what the photon did when it passed through the slits. This is called the delayed choice experiment, first proposed by John Wheeler in 1978 and experimentally confirmed multiple times since. The implications are staggering. The photon doesn't have a definite history until you measure it. You can retroactively determine what path it took. The past isn't fixed until you observe it. Wheeler took this further. He proposed a cosmic version. Light from a distant quasar can be bent by a galaxy acting as a gravitational lens. The light can take two different paths around the galaxy, call them Path A and Path B. By the time the light reaches Earth, billions of years have passed. Now we detect this light. We can choose to do a which path measurement, detecting which path each photon took. Or we can combine the light from both paths and look for interference. According to quantum mechanics, our choice made billions of years after the photon passed the galaxy determines whether it took one path or both. Wheeler wrote, "We are participants in bringing into being not only the near and here, but the far away and long ago." This has been tested with real quasars. The results confirm quantum mechanics. Our measurements today affect what paths photons took billions of years ago. The past is not fixed until we observe it. This is the quantum measurement problem in its full horror. The wave function describes superpositions, multiple possibilities existing simultaneously. Measurement collapses the wave function to one definite outcome. But what counts as a measurement? Where's the boundary between the quantum realm of superpositions and the classical realm of definite states? Does a photon stay in superposition until it hits your retina? Or does it collapse when it interacts with the screen? Or with the air molecules between the screen and your eye? Or when the electrical signal reaches your brain? Or when you become consciously aware of seeing it? Some physicists, most famously Eugene Wigner, suggested consciousness causes wave function collapse. The universe stays in superposition until a conscious observer looks at it. Most physicists find this appalling. It puts consciousness at the center of physics, suggests reality requires observers, and raises the question: what happened before conscious life evolved? Was the early universe in superposition for billions of years? The most popular alternative is the many worlds interpretation, proposed by Hugh Everett in 1957. According to many worlds, wave functions never collapse. When a photon reaches a detector, the universe splits. In one branch, the photon hit position A. In another branch, it hit position B. Both outcomes happen in separate, non-interacting branches of reality. Every quantum measurement splits the universe into multiple versions. There are branches where you're reading this sentence, branches where you stopped watching 10 minutes ago, branches where you never clicked on this video. If many worlds is correct, there's no special role for light. Photons aren't doing anything weird. They're evolving according to deterministic equations. It's just that reality is vastly larger than we thought, an ever-branching tree of parallel universes. But many worlds has its own problems. If universes split at every quantum event, and there are trillions upon trillions of quantum events every second, the number of universes becomes incomprehensibly vast. Where is all this information stored? What does it mean for universes to split? Do they actually exist? Or is this just mathematical convenience? Nobody knows. Both consciousness causes collapse and many worlds sound like science fiction, yet one of them might be true. Or perhaps both are wrong, and the answer is something we haven't imagined yet. Here's another interpretation that will bend your brain: the quantum Bayesian or cubism interpretation. This view says the wave function isn't describing reality at all. It's describing your information about reality, your subjective degrees of belief about what you'll observe. From this perspective, wave function collapse isn't a physical process. It's you updating your beliefs when you get new information. Different observers can have different wave functions for the same system, because they have different information. This sounds like reality is subjective, which is disturbing. But QBISTs argue there's still an objective reality. We're just describing our interface with it, not the thing itself. Light isn't in superposition out there in the world. Superposition is in our description. representing our uncertainty. The photon has definite properties. We just can't know them all simultaneously. This brings back Einstein's hidden variables by the back door, except it's now hidden from us in principle, not just in practice. But remember Bell's theorem? Hidden variable theories don't work unless they're non-local, allowing instantaneous influences across space. So even QBISM requires accepting that reality is fundamentally non-local, with mysterious connections between distant events. No matter which interpretation you choose, light forces you to accept something crazy. Here's the existential crisis physicists face. We have a mathematical formalism, quantum mechanics, that predicts experimental outcomes with perfect accuracy. The Schrödinger equation, the Heisenberg uncertainty principle, the Born rule for calculating probabilities, all of it works flawlessly. But ask what it means, and you get wildly different answers depending on which physicist you talk to. Some say parallel universes. Some say consciousness creates reality. Some say there's no reality, just experiences and correlations. Light is at the center of this crisis because light is what we use to observe the quantum world. Every experiment, every measurement involves photons carrying information from the quantum system to our detectors. We're using quantum objects to study quantum objects. We're using light to investigate light. It's like trying to see your own eyes without a mirror, an impossible act of self-reference. Stay with me. We're about to explore how light connects to information itself, and why that might be the key to everything. Let's shift perspectives entirely. What if light isn't primarily about energy or waves or particles? What if it's fundamentally about information? A photon traveling from a star to your eye carries information about the star's temperature, composition, motion, distance. Light is the universe's primary messenger, carrying data across cosmic distances. In 1948, Claude Shannon developed information theory, creating a mathematical framework for quantifying information. He defined information in terms of uncertainty reduction. If an event has only one possible outcome, it carries no information. You learn nothing. If an event has many possible outcomes, observing which one occurs gives you information. Now apply this to light. A photon carries information about its source. But quantum mechanics says the photon exists in superposition until observed. Before measurement, it doesn't have definite properties. So when does it acquire the information it carries? Only when you measure it. The information doesn't travel from the star to your eye. It materializes at the moment of observation. This leads to a radical idea proposed by physicist John Wheeler. It from bit. Wheeler suggested that information bits, quantum bits, choices between possibilities, is more fundamental than physical existence. He imagined the universe as a self-excited circuit. The universe brings itself into being through acts of observation. You look at a photon, collapsing its wave function, determining what it is. That photon came from an atom that also existed in superposition until something observed it. Tracing back, the universe is a vast network of observations calling each other into existence. Wheeler wrote, "The universe doesn't exist out there, independent of all acts of observation. It is in some sense a participatory universe." This sounds mystical, but it's rooted in the quantum measurement problem. If wave functions don't collapse until observed, and everything is described by wave functions, then reality is incomplete without observation. And light is the primary carrier of these reality-creating observations. Modern quantum information theory has formalized these ideas. Quantum entanglement, the phenomenon where measuring one particle instantly affects another, no matter how far apart, is now understood as a form of shared quantum information. Here's how entanglement works with photons. You can create two photons in an entangled state where their polarizations are correlated. Measure one is vertical, and the other will definitely measure horizontal, even if they're light years apart. Measure one is horizontal, and the other will be vertical. Einstein called this spooky action at a distance. and thought it proved quantum mechanics was incomplete. But experiments have confirmed it's real. Measuring one photon somehow affects its entangled partner instantaneously. But here's the twist. You can't use entanglement to send information faster than light. You see random results when measuring your photon. Only by comparing with the other person's measurements do you see the correlation. The information confirming the entanglement has to travel at light speed or slower. So entanglement doesn't violate relativity, but it does show that reality is non-local. Distant photons share a quantum state that can't be explained by properties each photon has independently. The information about their correlation isn't stored in either photon. It's stored in the relationship between them in the quantum state of the pair. This has led to quantum computing and quantum cryptography. Quantum computers use entangled quantum bits qubits that exist in superposition. They can process certain information much faster than classical computers because they explore many possibilities simultaneously, and photons are ideal qubits. They travel at light speed, carrying quantum information over long distances without decaying quickly. Researchers have achieved quantum teleportation, transferring the quantum state of one photon to another distant photon using entanglement and classical communication. This isn't Star Trek teleportation. You're not moving matter or energy faster than light. You're transferring quantum information, the pattern, the configuration, while the physical photon stays local. But even calling it information transfer is misleading. The quantum state isn't a thing that moves from A to B. It's more like the state ceases to exist at A and simultaneously exists at B, mediated by the shared entanglement. We lack the words to properly describe what's happening because quantum information doesn't behave like classical information. It can't be copied. It can't be fully known. It exists in superposition. It's shared non-locally through entanglement. Light is the carrier of this weird quantum information, and we're just beginning to harness its potential. If your brain hurts, good. That means you're actually understanding this. The people who tell you quantum mechanics is easy or intuitive are either lying or haven't thought deeply about it. Richard Feynman, one of the architects of quantum field theory, famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And light photons, electromagnetic radiation, quantum excitations of the electromagnetic field, is our clearest window into quantum mechanics because we can actually perform these experiments. We can send single photons through interferometers. We can entangle them. We can watch them behave in ways that defy classical intuition. Before we continue, take a moment. Like this video if you haven't already. Share it with someone who needs their mind expanded. Comment with your biggest question about light. I read every comment, and your question might shape my future videos. We're about to explore the cutting edge. What happens when you try to merge quantum mechanics with gravity? What happens to light near black holes? Can we ever truly understand what photons are? The answers, or lack thereof, are coming next. We have two magnificent theories describing the universe. General relativity describes gravity, space-time curvature, black holes, and the large-scale structure of the cosmos. Quantum mechanics describes atoms, particles, uncertainty, and superposition. Both theories are supremely successful in their domains, but they're fundamentally incompatible. General relativity is deterministic. Given the mass-energy distribution, Einstein's equations tell you exactly how space-time curves. Quantum mechanics is probabilistic. Given a system state, the Schrödinger equation tells you probabilities for different outcomes. General relativity is smooth, and continuous spacetime is a flexible fabric. Quantum mechanics is discrete, and granular energy comes in quanta. Particles jump between states. When you try to combine them, the equations explode. You get infinities that can't be removed. The mathematics breaks down. And light sits right at the boundary of this breakdown. Photons are quantum objects. They obey quantum mechanics. But they travel through spacetime, which is described by general relativity. How do photons interact with curved spacetime at the quantum level? We don't know. We don't have a theory of quantum gravity. Near black holes, this becomes critical. A black hole's event horizon is a point of no return. Even light can't escape from inside it. But quantum mechanics says black holes should radiate. Stephen Hawking proved this in 1974. Hawking radiation works like this. Near the event horizon, quantum fluctuations of the electromagnetic field create particle-antiparticle pairs. Normally, they annihilate immediately. But near the horizon, one can fall in while the other escapes. To an outside observer, the black hole appears to emit radiation photons and other particles. This is where things get weird. The radiation is thermal. It has a temperature inversely proportional to the black hole's mass. Smaller black holes are hotter. As a black hole radiates, it loses mass and gets hotter, radiating faster, losing mass faster, in a runaway process until it evaporates completely. But this creates a paradox. The information paradox goes like this. Quantum mechanics says information is never destroyed. If you know a system's state perfectly now, you can calculate its state in the future or past. Information is conserved. But if a black hole evaporates completely, what happens to the information about everything that fell in? The Hawking radiation is thermal random. It doesn't carry specific information about what formed the black hole. So information appears to be destroyed. This violates quantum mechanics. Physicists have proposed dozens of solutions. Maybe information is encoded in the radiation in subtle correlations. Maybe it's stored in the event horizon structure. Maybe black holes don't evaporate completely, they leave remnants. Maybe information escapes into other universes. Leonard Susskind and Gerard 't Hooft proposed the holographic principle. All the information about what's inside a black hole is encoded on its two-dimensional surface, like a hologram encoding three-dimensional information. This led to a shocking generalization. Perhaps our entire three-dimensional universe is a hologram. All the information about what's in this room, the atoms, the fields, the light might be encoded on a distant two-dimensional boundary surface. We think we live in 3 dimensions, but we might be patterns on a cosmic screen. Light plays a special role in this. Photons carry information out of gravitationally warped regions. The cosmic microwave background light left over from the early universe carries information about conditions 13.8 billion years ago, encoded in subtle temperature variations. Astronomers use light to peer into the past. Looking at a galaxy a billion light years away, you're seeing it as it was a billion years ago. The photons are time capsules, preserving information across cosmic distances. But if space-time itself is quantized, if there's a smallest possible length, the Planck length of y-35 meters, then space isn't infinitely divisible. It's grainy at unimaginably small scales. What does a photon do in quantized space-time? Does it hop from one quantum of space to the next? Does its wave function spread across discrete pixels of reality? How does continuous wave mechanics work in a discrete space? Nobody knows because we don't have quantum gravity. String theory attempts to solve this. It proposes that fundamental entities aren't point particles, but tiny vibrating strings. Different vibration modes correspond to different particles. One mode is the photon light is a string vibrating in a particular way. String theory naturally includes gravity. Another vibration mode is the graviton quantum of gravitational waves. So string theory unifies all forces, including gravity, in a quantum framework. But string theory has problems. It requires extra dimensions, not just the 3 of space and 1 of time we experience, but 6 or 7 additional dimensions, curled up at tiny scales. It has no unique solution. There are 10,500 different possible string theory configurations, called the string theory landscape, and it makes no testable predictions yet. We can't build accelerators powerful enough to probe the energy scales where string effects would appear. Loop quantum gravity is an alternative. It quantizes space-time itself, describing space as a network of discrete loops. Area and volume are quantized. Space-time is fundamentally granular. In loop quantum gravity, light propagates through this discrete structure. Photons might experience tiny delays depending on their energy, accumulating over cosmic distances. Astronomers have looked for these delays in gamma-ray bursts from distant galaxies. So far, nothing. Either the effect is too small, or loop quantum gravity is wrong. We're approaching the end of hour 2, and we've covered an enormous amount of ground. From the basics of light speed, to quantum information, to black holes, to string theory, and through it all, light has been the central mystery. Here's what's remarkable. Despite a century of quantum mechanics, despite detecting gravitational waves and photographing black holes, despite building quantum computers and quantum communication networks, we still can't answer the simple question. What is light? We have mathematical descriptions. We have predictions. We have technologies. But the fundamental nature of light, what it is, ontologically remains elusive. In the next section, we're going to explore cutting-edge experiments that are pushing light to its limits. We're going to see light behave in ways that challenge everything we've discussed. And we're going to confront the possibility that the question, what is light, might not have an answer. Stay with me. The journey is about to get even stranger. Let's talk about what happens when you push light to its limits: extreme intensities, extreme energies, extreme interactions. Modern lasers can create light more intense than anything in nature. The National Ignition Facility can focus 500 trillion watts of power onto a target the size of a pencil eraser for a few nanoseconds. That's more power than all the electricity used by humanity at that instant, concentrated into a tiny spot. What happens? The electromagnetic field becomes so strong that quantum fluctuations become real particles. Photons can spontaneously create electron-positron pairs from the vacuum. Light creates matter directly from empty space. This is predicted by quantum field theory, but was only recently observed directly. In 2022, researchers using the relativistic heavy ion collider created photon-photon collisions energetic enough to produce matter. Two photons collided and became an electron and positron, light becoming matter. E equals mc in its most direct form. But there's something even weirder. At extreme intensities, photons can interact with each other. In classical electromagnetism, light beams pass through each other without interacting. Shine two flashlight beams so they cross, and they don't affect each other. This is because photons are electrically neutral. They don't respond to electromagnetic fields. But in quantum electrodynamics, photons can interact indirectly. A photon can briefly create a virtual electron-positron pair. Another photon interacts with this virtual pair. The net effect is photons scattering off each other, photon-photon scattering. This is incredibly rare. The probability is tiny, proportional to the fine structure constant, about 1/137th, raised to the fourth power, roughly 1 in 400 million for each interaction. But with intense enough light, it becomes measurable. Experiments at facilities like the European XFEL are searching for this effect. Finding it would confirm a prediction of quantum electrodynamics made decades ago but never directly observed. Light can interact with itself. The electromagnetic field is subtly nonlinear at the quantum level. Then there's the Schwinger limit. At field strengths of about yp volts per meter, the vacuum itself becomes unstable. Virtual particle pairs become real, even without photons colliding. This is the field strength where quantum mechanics tears space-time apart, spontaneously creating matter from nothing. We can't create these fields yet. It would require laser intensities thousands of times beyond current technology. But such fields exist near the surfaces of magnetars, neutron stars, with magnetic fields trillions of times stronger than Earth's. In magnetar magnetospheres, the vacuum is constantly breaking down, creating a plasma of particles from nothing. Light near a magnetar behaves completely differently than anywhere else. Photons split into multiple lower energy photons. Photons change polarization randomly. The vacuum birefringes becomes directionally dependent, like a crystal, because virtual particles align with the magnetic field. We've observed these effects in magnetar observations. Light is revealing the quantum nature of the vacuum in the most extreme environments in the universe. Let's go faster. What happens to light when it moves through exotic materials? In 2021, researchers slowed light to 38 miles per hour in ultra-cold sodium atoms. The atoms absorb and re-emit photons in a coordinated way that dramatically slows the light's group velocity, the speed at which information propagates. Other experiments have stopped light completely, storing its quantum state in atomic excitations, then releasing it later. Light goes in, disappears, and reappears seconds later with its quantum information intact. But here's the weird part. Even when light is stopped, the photons aren't at rest. There's no such thing as a stationary photon. What's really happening is the photons are being absorbed, and their quantum state is mapped onto atoms. Then new photons are created with the same state. The light that comes out isn't the same light that went in. It's new light, but with the same quantum information? This raises a philosophical question. Is a photon defined by its quantum information, or by its physical continuity? If you perfectly recreate a photon's quantum state, is it the same photon? Or does identity require spatiotemporal continuity? In other materials, light can be made to travel faster than light. Wait, what? This doesn't violate relativity because it's the phase velocity or group velocity exceeding c, not the signal velocity. Information still propagates at c or slower. Here's how it works. In certain materials with anomalous dispersion, a pulse of light appears to exit before it enters. The peak of the pulse arrives at the detector before it entered the material. Time reversal? No. The pulse is reshaping as it travels, and what emerges is a reconstructed version based on the leading edge of what entered. No information travels faster than c, but it looks like it does if you're not careful about what you're measuring. These experiments highlight how slippery the concept of speed of light becomes when light interacts with matter. The speed depends on what aspect of the light you're measuring and what you mean by the light. We're 2 hours in, and I want to give you a moment to process. The list of weird things light does keeps growing. Exists in superposition until observed. Doesn't experience time or space from its own reference frame. Creates matter from vacuum at high intensities. Interacts with itself through quantum loops. Can be slowed, stopped, or appear to exceed its own speed limit. Carries quantum information that can be teleported, and we haven't even talked about the deepest mystery yet. Consciousness. How do photons hitting your retina become subjective experience? How does electromagnetic radiation become the vivid colors, the brightness, the visual world you experience? This is the hard problem of consciousness, and light is at its center. We're going there next. Make sure you're subscribed. Let me shift gears. For the last 2 hours, we've been talking about light as physicists do mathematically, experimentally, abstractly. But light isn't abstract to you. Light is how you're experiencing this moment. Every color you see is light of different wavelengths. Red is about 700 nanometers. Violet is about 400 nanometers. But here's the thing. Wavelength is an objective property. It's just the spatial period of oscillation in the electromagnetic field. Color is subjective. It's your brain's interpretation of that wavelength. There's nothing inherently red about 700 nanometer light. It's just an electromagnetic wave. Your brain could have chosen to interpret it as green or blue. The mapping between wavelength and color is arbitrary a convention established by your neural architecture. Some people are tetrachromats. They have 4 types of color receptors instead of 3. They see colors you can't. Mantis shrimp have 16 types of color receptors. They experience a rainbow you can't even imagine. What is color, really? It's not in the light. It's not in the world. It's in your experience. This is the hard problem of consciousness, articulated by philosopher David Chalmers. How do physical processes, photons hitting rhodopsin molecules in your retina, triggering electrical signals in neurons, become subjective experience? There's an explanatory gap. You can describe the physics of light, the biology of vision, the neuroscience of visual processing. But none of that explains why there's something it's like to see red. Why isn't the visual processing happening in the dark, producing behavior without experience? Some philosophers argue experience is fundamental panpsychism, the idea that consciousness is a basic feature of the universe, like mass or charge. Maybe photons have primitive experiential properties that combine when they interact with complex systems like brains. Most neuroscientists find this absurd. They believe consciousness emerges from information processing. That subjective experience is what complex computation feels like from the inside. But nobody has solved the hard problem. Nobody has explained how or why physical processes generate subjective experience. Here's what's fascinating. Light is the bridge. It's the physical phenomenon that mediates your conscious experience of the external world. Right now, photons are bouncing off objects, carrying information about their shape, color, texture. These photons enter your eyes, are focused by your lens, and strike your retina. There, they're absorbed by molecules that change shape, triggering a cascade of biochemical reactions, ultimately producing electrical signals that travel through your optic nerve to your brain. Your brain reconstructs a three-dimensional visual scene from these signals, adding colors, inferring depth, recognizing objects, attributing meaning. What you're seeing isn't out there. It's a model your brain constructs based on limited information carried by light. You're not seeing reality directly. You're seeing your brain's interpretation of light patterns. This is why optical illusions work. Your brain makes assumptions about how light behaves, assumptions usually correct, but occasionally wrong. When the light pattern violates those assumptions, you see impossible objects, motion where there is none, colors that don't exist in the image. Your visual experience is a controlled hallucination, with light as the constraint keeping it anchored to reality. But let's go deeper. Your sense of self, your feeling of being a unified observer, might be intimately connected to light. You feel like there's a single you watching the world through your eyes. But neuroscience reveals that's an illusion. Your brain is a massively parallel network of specialized modules. Visual processing alone involves dozens of separate brain regions, each handling different aspects: color, motion, edges, faces, objects. These separate processes are bound together into a unified experience. You don't see color in one stream and motion in another. You see colored objects moving. This is called the binding problem, and nobody knows how the brain solves it. Some researchers think temporal synchronization is key: different brain regions processing the same object fire in sync, creating the experience of unity. The gamma rhythm neural oscillations around 40 Hz might be the brain's way of saying these signals belong together. But what establishes this synchronization? Some evidence suggests it's driven by attention, which itself might be modulated by feedback loops involving the thalamus, a brain region that acts like a relay station for sensory information, including light signals from the retina. Light is not just what you see. It might be structuring how you experience being a self. Here's an analogy that might help. Think of your visual experience as a movie playing in your mind, but there's no screen and no audience. The movie is playing itself into existence, moment by moment, using light from the external world as a script, but improvising and filling in details based on expectations and memories. And the you watching the movie? That's also part of the movie. The observer is observed. The self watching the visual field is itself a construction of the visual cortex and other brain systems. This isn't mysticism. This is what neuroscience tells us. Your sense of being a coherent self, located behind your eyes, watching the world, that's a useful fiction your brain creates to coordinate behavior. And light is the primary input into this fiction. When you see a sunset, what's really happening? Photons of various wavelengths are hitting your retina. Your brain interprets short wavelengths as blue, long wavelengths as red. It infers the sun is low because the light is reddened by passing through more atmosphere. It accesses memories and emotions associated with sunset's tranquility, endings, beauty. The experience of the sunset, the glowing oranges and pinks, the aesthetic appreciation, the emotional resonance, none of that is in the photons. It's all added by your brain. Yet it feels immediate and real. You don't experience it as interpretation. You experience it as direct perception. Let me ask you something personal. When was the last time you really looked at light? Not used it to see objects, but actually paid attention to the light itself. Next time you're outside, try it. Look at how light filters through leaves, creating dappled patterns. Notice how it refracts through water droplets, creating rainbows. Observe how shadows have color. They're not just absence of light, but illumination by scattered blue light from the sky. Light is everywhere, mediating every visual experience, yet we rarely notice it. We see through it to objects and scenes. Making light itself the object of attention requires a shift in perspective. And maybe that's a metaphor for understanding light scientifically. We use light as a tool to see atoms, to detect distant galaxies, to transmit information. But understanding light itself requires stepping back and asking what it is we're using, not just what we're using it for. We're in the final stretch. The last sections will tie everything together, revealing why light's mysteries matter and what they tell us about the nature of reality itself. Let me step back and address the core question. Why has light been so uniquely difficult for scientists to explain? I think there are 5 fundamental reasons, and they reveal something profound about the limits of human understanding. First, light bridges the quantum and classical worlds. It's quantum. It comes in discrete photons, exhibits superposition and entanglement. But it's also macroscopic. We see and use light in everyday life. Most quantum phenomena happen at scales too small to observe directly. Light is the exception. We interact with quantum objects whenever we see. This makes light's weirdness impossible to ignore. You can't wave away quantum mechanics as irrelevant to daily experience when the light entering your eye right now exists in superposition until the moment it hits your retina. Second, light is the universal messenger. Every experimental measurement of quantum systems involves photons carrying information from the system to the detector. We can't observe quantum systems directly. We observe light they emit or absorb or scatter. This creates a fundamental circularity. We're using light to study light. We're using quantum objects to measure quantum objects. We can never step outside this system to observe it objectively. It's like trying to see your own face without a mirror. You can see reflections, photographs, representations mediated by light. But you cannot see your face directly because your eyes are part of your face. Similarly, we cannot observe light directly because all observation is mediated by light or other quantum phenomena. We're trapped inside the system we're trying to understand. Third, light challenges our intuitions about causality and time. Because photons don't experience time, the usual story we tell about cause and effect breaks down. We think of events as having a temporal order. Cause precedes effect. But for light, emission and absorption are simultaneous. There is no journey, no duration between cause and effect. This violates our deep intuition that things happen in sequence. Light reveals that temporal sequence is frame-dependent, observer-relative. What seems sequential to us is simultaneous to the photon. This makes light a window into space-time's fundamental structure, and that structure is nothing like our intuitive picture of three-dimensional space persisting through time. Fourth, light is massless. This seems like a detail, but it's profound. Mass is resistance to acceleration. Massless particles don't resist. They immediately move at maximum speed, c, regardless of energy. But mass is also what gives particles rest frames. Reference frames where the particle is at rest. Photons have no rest frame. There's no perspective from which light is stationary. This makes photons fundamentally different from every particle with mass. And it raises a question. Do photons really exist in the way massive particles do? Massive particles persist. They have a world line through spacetime, a trajectory from birth to destruction. Photons don't have world lines in the usual sense. They're more like instantaneous connections between events. Maybe photons aren't things that move. Maybe they're the structure of spacetime itself, the fundamental relationships between events, dressed up as particles by our measurement apparatus. Fifth, light is both real and abstract. Photons have measurable effects. They carry energy, momentum, angular momentum. They can be absorbed, emitted, scattered. They're as real as billiard balls in that sense. But photons are also excitations of an abstract quantum field, the electromagnetic field. And that field isn't made of anything. It's a mathematical structure, assigning complex numbers to every point in spacetime. So what are photons? Are they concrete objects? Or are they mathematical abstractions that happen to have physical effects? This ambiguity runs through all of quantum field theory. We have equations that predict observations. But what the equations describe, whether they represent real entities or just calculational tools, remains controversial. Light forces this question into the open because we interact with light directly. We can't avoid asking what it is. And we don't have a satisfying answer. These 5 reasons compound. Light is quantum yet macroscopic, the tool we use to observe itself, challenges causality, has no rest frame, and is ambiguously real, abstract. Any one of these would make light hard to understand. Together, they make light's nature perhaps the deepest mystery in physics. But here's the thing. This isn't a failure of science. It's a revelation about the nature of understanding itself. Science works by building model-simplified descriptions that capture essential features and predict observations. We never explain things completely. We explain them well enough to predict and control. Light shows us the limits of this approach. We have spectacular models of light Maxwell's equations, quantum electrodynamics, the Standard Model. These models predict experimental results to 15 decimal places. But do they tell us what light is? Or just how it behaves? Maybe that's all understanding can ever be. Not grasping the essential nature of things, but having good models that relate observations to each other. Science gives us maps, not territories. Or maybe we're missing something fundamental. Maybe there's a deeper theory waiting to be discovered: quantum gravity, string theory, loop quantum gravity, or something completely new that will finally make sense of light. Some physicists think the key is information. Maybe the universe is fundamentally made of information, and what we call matter and energy are particular configurations of information. From this perspective, photons are information carriers, because that's all they are, pure information, free of the burden of mass. Others think the key is geometry. Maybe spacetime isn't fundamental. Maybe it emerges from something more basic: quantum entanglement, perhaps. Photons would then be excitations of this emergent spacetime, not fundamental themselves. Still others think we need a radically new concept, something as different from quantum mechanics as quantum mechanics was from classical physics. Maybe the answer requires mathematical or conceptual tools we haven't invented yet. We're approaching the end of this journey, and I want to acknowledge something. If you're feeling confused or overwhelmed, that's appropriate. That's the correct response to light's mysteries. Einstein spent the second half of his life struggling with quantum mechanics, never fully accepting it. Bohr and Heisenberg developed quantum mechanics, but disagreed about what it meant. Feynman mastered quantum electrodynamics and still said nobody understands it. If the greatest physicists of the 20th century struggled with this, it's okay if you do too. But here's what's amazing. You now know more about light than 99.9% of people who've ever lived. You understand that light is quantum mechanical, that it's both wave and particle, that it doesn't experience time, that it carries quantum information, that it behaves differently when observed. You've grappled with the measurement problem, entanglement, relativity, quantum field theory, and the information paradox. You've confronted the hard problem of consciousness and the limits of scientific explanation. That's incredible. You should feel proud. Now let's bring it all home. So why do scientists struggle to explain light? The answer, ultimately, is this. Light is the boundary between the knowable and unknowable. Light is how we know anything about the external world. It carries information from distant stars, from the atoms in your body, from the screen in front of you. All our scientific knowledge ultimately traces back to photons, delivering data to our instruments and eyes. But light is also what prevents us from knowing reality directly. We can't observe the universe unfiltered. We observe light and infer the universe from that. We're seeing shadows on the cave wall, not the things casting the shadows. And when we turn our instruments on light itself, trying to understand what it is, we encounter reflexivity. We use light to study light. We use quantum mechanics to describe quantum phenomena. The tool and the object of study are the same, creating an irreducible circularity. Here's my attempt at synthesis. Light is a quantum field excitation that connects events in spacetime, carrying information in a way that respects both quantum mechanics and relativity. It exhibits wave-like behavior in propagation and particle-like behavior in interaction. It exists in superposition until measurement, at which point chooses definite properties through a process we don't fully understand. From its own reference frame, light doesn't travel. Emission and absorption are instantaneous. From our reference frame, light propagates at finite speed, creating the structure of causality. Light is real. It carries energy and momentum, creates and destroys particles, structures the vacuum. But it's also abstract, a mathematical pattern in a quantum field, a configuration of information, a relationship between events rather than a thing that moves. That's the best I can do. And I suspect that's the best anyone can do without a theory of quantum gravity or a solution to the measurement problem or a revolution in our understanding of information and consciousness. But maybe struggling to explain light isn't a bug, it's a feature. Maybe the universe is telling us something important through light's mysterious nature. Perhaps the lesson is humility. We're clever apes who've learned to manipulate electromagnetic radiation, splitting atoms and communicating across planets. But the fundamental nature of the universe remains elusive, hinted at, but never fully grasped. Perhaps the lesson is about the nature of reality. The universe isn't made of objects moving through space and time. It's made of fields, relationships, information, possibilities collapsing into actualities. Light's weirdness is revealing the weirdness of existence itself. Perhaps the lesson is about consciousness. The hard problem of consciousness and the measurement problem in quantum mechanics might be connected. Maybe observation, consciousness, and physical collapse are linked in ways we don't understand. Light is where this connection is most apparent. Or perhaps light is telling us that explanation has limits. Not everything can be reduced to simpler components. At some point, you hit fundamental entities that just are. They have properties that can be described, but not explained in terms of something more basic. Maybe photons are fundamental, and asking, what is a photon really, is like asking, what is existence really? There might not be an answer more satisfying than, that's what existence is. Photons exist. They have these properties. They obey these equations. That's the ground floor. This can feel unsatisfying. We want reality to make sense to fit our intuitions about objects, motion, cause, and effect. But maybe reality doesn't care about our intuitions. Maybe it just is what it is, and our job is to describe it accurately, not make it comfortable. So what does all this mean for you? Why should you care about light's mysteries? First, it's intellectually honest. The universe is weird. Pretending it makes sense when it doesn't is comforting but false. Embracing the weirdness, sitting with the discomfort of not knowing, is more truthful. Second, it's philosophically important. Questions about light connect to questions about reality, knowledge, consciousness, and existence. These aren't just physics problems. They're fundamental questions humans have asked for millennia. Third, it's practically relevant. Quantum technologies, quantum computers, quantum cryptography, quantum sensors are based on light's weird quantum properties. Understanding these properties, even imperfectly, will shape the technologies defining the 21st century. Fourth, it's aesthetically beautiful. The equations describing light Maxwell's equations, the Dirac equation, quantum electrodynamics, are among the most elegant in all of science. There's beauty in the mathematics, even if the meaning remains elusive. But most importantly, light's mysteries remind us that there's more to reality than meets the eye. Literally, you look at the world and see objects, colors, motion. It seems obvious mundane, but underlying that everyday experience is quantum superposition, electromagnetic fields, space-time curvature, information encoded in photon states, the hard problem of consciousness. Reality is radically stranger than it appears, and light is the medium through which that strangeness manifests. Every time you see a rainbow, you're watching light split into its component frequencies, each wavelength refracted slightly differently by water droplets. That's beautiful. But it's also quantum mechanical. Each photon in that rainbow is a discrete quantum of energy, existing in superposition until it hits your eye, collapsing into a definite state only at that moment. Every rainbow is a quantum phenomenon masquerading as classical beauty. Let me tell you a story. In 1905, Albert Einstein published 4 papers, each revolutionary. One explained the photoelectric effect, introducing photons. One explained Brownian motion, proving atoms exist. One developed special relativity, unifying space and time. One derived E equals mc, showing mass and energy are interchangeable. Later, Einstein said that of all his work, he'd spent the most time thinking about light. Not relativity, not mass-energy equivalence light. He called photons spooky and never fully accepted quantum mechanics, despite essentially founding it. If Einstein, arguably the most brilliant physicist who ever lived, couldn't make sense of light, what hope do we have? But that's not the right question. The right question is, what does it mean that reality is so strange that even Einstein couldn't fully grasp it? It means the universe is deeper than any human mind can fully comprehend. But it also means there's always more to discover, always deeper mysteries waiting. Here's what I want you to take away from these 3 hours. Light is the most familiar and most mysterious phenomenon in the universe. You interact with it constantly, yet it violates your intuitions about how reality works. Scientists have made spectacular progress understanding light's behavior. We can predict exactly how light will interact with matter, how it propagates through space, how it creates interference patterns. But we don't know what light is. We don't know why it exists. We don't know how quantum superposition becomes definite reality. We don't know if photons are truly fundamental or emergent. We don't know how electromagnetic fields relate to consciousness. These aren't failings of science. They're the frontier. This is where human knowledge ends and mystery begins. And light sits right at that boundary, illuminating the darkness while remaining fundamentally mysterious itself. If you've made it this far 3 full hours, you're amazing. You've engaged with some of the deepest questions in physics, philosophy, and consciousness. You've confronted ideas that challenge everything you thought you knew about reality. Before I wrap up, I need you to do something. Not for me, for yourself. Share this video with someone who loves learning. Not because I need views, but because these ideas deserve to spread. Too few people know that reality is this weird, this mysterious, this profound. And leave a comment. Tell me, what was the biggest mind blow for you? Which interpretation of quantum mechanics do you lean toward? Do you think we'll ever truly understand light? What question do you still have? I read every comment, and your questions often inspire future videos. Subscribe if you haven't, because we're doing more deep dives like this. Next time, why does mathematics work so unreasonably well in describing the universe? It's another 3-hour journey into mystery. Let me end with one final thought. Light connects you to the universe in ways that are both profound and literal. When you look at the night sky, photons that traveled for years or millennia or millions of years are ending their journey in your eye. You're connected across vast space and time to distant stars, dead civilizations, the early universe itself. The cosmic microwave background light from 380,000 years after the Big Bang is hitting your eye right now. You're literally seeing the afterglow of creation, stretched and cooled, but still present, connecting you directly to the moment when the universe became transparent to light. Every photon in your body was created somewhere in stars, in the Big Bang, in radioactive decay, in chemical reactions. You are made of light, in a sense. When matter and antimatter annihilate, they become pure light. When light has enough energy, it becomes matter. You're a configuration of quantum fields that used to be light and will be light again. The ancient Egyptians worshipped Re, the sun god, believing light was divine. They weren't scientifically correct, but they weren't entirely wrong either. Light is, in some sense, sacred not because gods created it, but because it's the fundamental connection between all things. Light doesn't experience the separation between events that you do. From light's perspective, the Big Bang and the heat death of the universe are the same moment. Everything that ever was or will be exists simultaneously in light's frame of reference. You are separated from distant events by space and time. Light is not. Light connects all moments, all places. It's the structure that relates one event to another, the medium through which cause affects effect. Without light, the universe would be a collection of isolated events with no relationships. Light creates the web of connections that makes the universe coherent. So when scientists struggle to explain light, they're struggling to explain how the universe hangs together. They're asking, what is the fundamental nature of connection itself? And maybe that's a question that can't be fully answered. Maybe connection is the ground floor, the fundamental given that can't be reduced further. If so, light isn't a thing. It's the relationship between things. It's not part of reality. It's the structure that makes reality possible. From this perspective, asking, what is light, is like asking, what is existence? Or, why is there something rather than nothing? These are questions at the absolute boundary of inquiry, where science, philosophy, and mystery blur together. We can describe light mathematically. We can predict its behavior. We can harness it technologically. But understanding its fundamental nature might require transcending the human perspective, entirely seeing from a viewpoint that doesn't privilege objects, time, or space. And we can't do that. We're embedded in space-time. We experience duration and separation. We can't step outside to see reality as it truly is, if truly even means anything. But that's okay. Science isn't about achieving complete understanding. It's about building better and better models, asking deeper and deeper questions, pushing the boundaries of the knowable. Every generation of physicists thought they were close to a final theory. Newton thought classical mechanics was nearly complete. 19th century physicists thought Maxwell's equations were the end of the story. 20th century physicists thought quantum mechanics and relativity would unite soon. They were all wrong. Every answer revealed deeper questions. Light will continue to surprise us. Quantum gravity, when we finally develop it, will reveal new aspects of light's nature we can't currently imagine. Technologies we build will expose phenomena we don't expect. The mystery won't end. It will just deepen. And that's wonderful. That's what makes science exciting. There's always more to discover, always deeper levels of reality to explore. Light has guided that exploration for centuries, from Newton's prisms to Maxwell's equations to Einstein's photons to quantum field theory. It will guide future explorations too. So the next time you see a beam of sunlight streaming through a window, pause. Really look at it. Think about what you now know. That light is quantum mechanical, existing in superposition until observed. That it doesn't experience the journey from sun to your eye from its perspective. Emission and absorption are simultaneous. That it's an excitation of the electromagnetic field, carrying energy and information. That it mediates your entire visual experience of reality, yet you can't see it directly, only its effects. That light is both the most studied and least understood phenomenon in the universe. That the brightest minds in history have grappled with its mysteries and been humbled. That we've built civilization on technologies using light while still not knowing what light fundamentally is, and feel the wonder. Not the comfortable wonder of having answers, but the profound wonder of confronting genuine mystery questions that matter. Questions we're working on, but questions that remain open. Light teaches us humility. It teaches us that reality doesn't conform to human intuitions. It teaches us that the universe is stranger and deeper than we imagined. But it also teaches us that we can make progress. We can build models that work, even if we don't fully understand why they work. We can harness phenomena we don't fully comprehend. We can push the boundaries of knowledge incrementally, generation after generation. That's the human project, not to achieve complete understanding, but to continually expand the circle of the known, always aware that the unknown surrounds us. Why do scientists struggle to explain light? Because light reveals the limits of explanation. Because light connects us to questions about reality, consciousness, time, information, and existence that we're not yet equipped to answer fully. But struggle isn't failure. Struggle is the process. The greatest physicists struggled with light because light matters. The questions it raises are worth struggling with. And now you've struggled with them too. You've spent 3 hours confronting ideas that challenge your worldview. You've engaged with genuine intellectual difficulty. You've allowed your mind to be changed, expanded, humbled. That's rare and valuable. Most people avoid discomfort. They want simple answers, comfortable certainties. You chose confusion and mystery instead. That takes courage. And it puts you in good company alongside every scientist, philosopher, and curious person who's ever looked at light and asked, "What are you really?" We don't know, but we're working on it. And maybe, decades or centuries from now, someone will look back on this moment the way we look back on ancient philosophers arguing about whether eyes emit light. They'll have answers we can't imagine. They'll have conceptual tools that make our struggles seem quaint. They'll have unified light, gravity, quantum mechanics, and consciousness into a single elegant framework that makes everything clear. Or maybe they'll be even more confused, because every answer revealed 10 new questions. Either way, the journey continues. The mystery deepens, and light keeps shining, connecting us to each other and to the cosmos, mysterious and beautiful and fundamental. Thank you for taking this journey with me. Thank you for caring enough to think hard about difficult ideas. Thank you for 3 hours of your attention. That's a precious gift in this distracted age. If this video changed how you see reality, share it. If it raised questions, comment. If you want more, subscribe. And the next time you see light, really see it, not just use it. Remember, you're looking at something that has puzzled the greatest minds in history and will puzzle minds for generations to come. That's not a weakness. That's a feature. Reality is endlessly fascinating because it's endlessly mysterious. Never stop asking why.